All right, this is the third video for our thermodynamics sequence and the last one, and it's really just 4 pages of notes that I have, but there's quite a bit of detail here, so figured I'd do a separate video for that. Anyway, let me do a little summary of the last problem from video 2. So we were looking at ammonia, and that was in the gas phase, CO2 in the gas phase, forming urea, solid, plus H2O liquid. And the delta G values that you can get from the tables were given in the last problem, and it was -17, -395, -199, and -237. So we calculated delta G for the reaction, and that was equal to -199 plus -237 minus 2 times -17 plus a -395, products minus reactants, and that equals -7.13 kilojoules per mole. So we had that from the last problem. I think that's pretty much where we ended. So here we can continue along with this one and next calculate K, the equilibrium constant. I showed you the equation. Maybe it was in the first thermo video. Maybe it was the second one. Delta G for the reaction is -RT logarithm of K. Now K, if you do kind of a rigorous derivation of this equation, it turns out that it's Kp. Now, if there are no gases present, then it's going to be equal to Kc. But in general, Kp, and I don't really care so much about it unless I specifically say Kp. You know, I just call it K. That's fine with me. But in any event, let's go ahead with this, calculating Kp. All right, so then you can use -7.13 kilojoules per mole, that's delta G, and then -8.314 joules per mole per Kelvin, and then you have to divide that by 1,000 joules per kilojoule. So you have, oh, wait a minute, yeah, that's right. And then times 298, that was to get them both in joules. And then you have, no, I'm wrong, get them both in kilojoules. All right, 298 Kelvin, and then logarithm of Kp. Now, if you go through that, you're going to solve for Kp, and that is 17.8. So next, if we wanted to go to Kc from here, so calculate Kc from Kp, then we would use the equation that we talked about earlier on our equilibrium chapters. Kp is equal to Kc times RT to the power delta N. So then R, if you recall, is 0.08206. It's important. It's important that you use that. And let's see, if we want to get Kc, we're going to have to solve for it. First of all, what is delta N for the reaction? So delta N, you have to go back up to look at the stoichiometry for this, and you got 1 plus 1 minus 2 minus 1. That's where that comes from. So 1 plus 1 for the products, and then you say -2 minus 1 for the reactants. So this is 2 minus 3, so it's equal to -1. All right, so then you can plug that in. You can say Kp is Kc times RT to the negative 1. We want to calculate Kc, so this is going to be equal to Kp. And then we're going to divide by RT to the minus 1, which will put RT in the numerator here. Okay, so we're going to divide. We're dividing right here. We're saying 1 over RT is RT to the minus 1. And then we're going to divide that by both sides. So that's going to flip RT up into the numerator. All right, that's going to be Kc. In our case, it's delta N is negative 1. So now we can plug in the numbers here. We have 17.8 for Kp. R is going to be 0.08206 liter atmosphere per mole Kelvin. And this is one where the units don't work out at all. You just ignore them completely. Don't even put them in. I put them in kind of by habit, but it's better to not even do that. Let's get rid of them. Long story. Kc then is equal to 435. All right, so we have values of delta G and K, and now we want to, so delta G is negative 7.13, Kp is 17.8, and Kc is 435. So I want to go back now to the criteria that we talked about for spontaneity for equilibrium constant K, and compare that to our delta G now. So you may recall that if K is greater than 1,000, then this is a product favored reaction. If K is less than 10 to the minus 3, it's a reactant favored reaction. Excuse me. And then if it's in between 10 to the minus 3 and 10 to the third, then you have both reactant and product present. And yeah, you could say that this is when the system's at equilibrium, when you got everything there. All right, now our this urea problem here, we have Kp is equal to 17.8, and so 17.8 is in between 1,000 and 10 to the minus 3. So that's going to be the situation where you have reactant and product present. Even if you used Kc, right, so Kc would be equal to 435. That's still within the same range, right? So it's in between 1,000 and 1,000th. So you'd say for our system then, for this urea problem, that R and P, R plus P are present. Systems at equilibrium. All right, let's see if our delta G values are consistent with that. So for delta G now, the old criteria, I'm going to give you an updated criteria as well. So the old criteria is that if delta G is less than negative 10 kilojoules, well, let me back up and say, first of all, if delta G is negative, right, then it's spontaneous, right? If delta G is positive, non-spontaneous. And if it's in between, then if it's 0, the system's at equilibrium. So anyway, that's true. There's nothing wrong with what we've done here. We've just kind of focused in some of the earlier analyses on whether delta G is negative or positive, or if it's 0. But you can look at numbers as well. So if you're going to use numbers instead, this is where I was going over here. So if delta G is less than negative 10 kilojoules, then it is spontaneous. So this is just the same kind of criteria as above, but more specific here. And then if delta G is greater than 10 kilojoules, then that would be non-spontaneous. And then there's this in-between region. So if it's in between negative 10 and positive 10 kilojoules, then it would be at equilibrium again, where you have the reactant and the product present. So for our system, delta G for this particular reaction, it was negative 7.13 for the formation of urea. So this puts it right in the middle again, right? So it's in between 10 kilojoules and negative 10 kilojoules. And so this is consistent with what we said earlier, that it's at equilibrium and reactant and product are present. All right, now if you use the equation delta G is negative RT log K. So if you actually put in your value of K, let me restate that. Yeah, if you put in your value of K here as being 10 to the third, delta G is going to be negative 17. If you put in 10 to the minus 3, delta G is going to be plus 17. It's not 10. This is kind of some arbitrary criteria here, 10 and negative 10. If you actually put the values in, these are the criteria for spontaneity, or forward reaction and reverse reaction, spontaneity and non-spontaneity. You don't get 10, you get 17. So, you could rewrite that and say, that, delta G less than negative 17 is spontaneous, delta G greater than 17 non-spontaneous, and then you could do that again, negative 17 and positive 17 reactant plus product. So what's the big difference? Not a lot. Not a lot. It's kind of a gray area. There's no, there's no line here that says it is or it isn't. These are just numbers that we kind of use, we throw out there. You get an idea about the magnitude and the direction of the reactant. But the whole point here is that it was consistent, that they're consistent. All right, now the other thing about this reaction before I move away, I'm on the second page. I'll put it on the third page. So if we look at this again, this system, now this is back to the second video here. This was the case of negative, if you recall. And the entropy for this reaction from the last video is equal to negative 0.04244 kilojoules per degree Kelvin, and the enthalpy for the reaction we calculated was negative 133.6 kilojoules. And of course delta G we just looked at again, and that's the negative 7.1. So this is the case of negative, and we have talked about this a little bit. This is a situation where it is spontaneous at low temperature and non-spontaneous at high temperature. So you heat it up and the reaction shuts off. And that's because this entropy factor is getting larger and larger because or the T delta S term is getting larger and larger because you're multiplying this number times the temperature. So it's kind of the disorder that's being created is what shuts down the reaction. Think of it that way. All right, so then, oops, one more. So the equation delta G is equal to delta H minus T delta S. This is the case where delta H is negative and you're subtracting a positive times a negative. And so this term is positive and is important when the temperature is high. So that's positive and this is negative, right? So which one predominates depends on what the temperature is. So you could say that when the temperature is small, comma, delta G is negative. And I'm going to make a list of 3 things here. The third one is when the temperature is large, delta G is positive. Okay, but what about the in-between situation? So what about when the numerical value of T delta S equals the numerical value of delta H? So there's that unique situation where they're equal and delta G is 0, right? So that's the second point here, or the middle point. When temperature is such that the 2 terms are equal, then delta G is 0. Okay, that's an important point. So, in other words, you start at low temperature, it's spontaneous. You're going to heat it up to a certain temperature such that these 2 terms are equal, and then any temperature higher than that will make delta G positive and the reaction shuts down. It's non-spontaneous. So in other words, what is the temperature here is called the transition temperature. So it transitions from spontaneous to non-spontaneous at a certain temperature as you continue to heat it up. That's the idea. So you can take that idea and say 0 is equal to delta H minus T delta S. Solve for T. I dropped the reaction there, but I just didn't want to drag it around. So this is negative 133.6 kilojoules per mole. And then that's delta H. The entropy is negative 0.04244 kilojoules per Kelvin per mole. Sometimes I leave out the per mole. And that turns out to be 315 degrees Kelvin. All right, so just to continue this a little bit more, it's kind of an interesting thing here. At 298 Kelvin, delta G is equal to negative 133.6, I'll leave out the units here, minus 298 times negative 0.04244, and that is equal to negative 7.1 kilojoules, which we've been looking at. If you get to 315 Kelvin, then delta G is equal to negative 133.6 minus 315 Kelvin times negative 0.04244. That's equal to 0, right? And then just pick some arbitrary higher temperature, greater than 315, we'll say 400 Kelvin, why not? Delta G here is negative 133.6 minus 400 times negative 0.04244, and this is plus 36. So you can see from this that at temperatures below the transition temperature, it's spontaneous because delta G is negative. at the transition temperature, delta G is 0. And above the transition temperature, then delta G is positive, non-spontaneous, and you have the idea that the entropy term is kind of taken over, the system's coming disordered, and the reaction shuts down. All right, so that is a really nice example there. And I've got another example that's very similar, and I thought we'd go through that too at the higher temperature. This one is the case of positive, positive. So case of positive, positive, that's a comma, fix that. And we can go through it quickly. More detailed problem here. Okay, we want to calculate Kp for the reaction at 1000 degrees C, which is 1273 Kelvin. And the reaction is calcium carbonate, which you can heat up, and it'll spontaneously go to calcium oxide plus CO2. All right, so we are given, and from our tables, delta H. It's called delta of H of formation, by the way. I kind of skipped that topic, but look in the tables, you see a little F there, formation. You can look that up or ask me about that. These are in kilojoules per mole. Okay. Then absolute values of S. These are, the symbol is SF formation. Let's just leave that out. And those are in joules per Kelvin per mole. And this one is 92.9, 38.2 to 13.7. All right, so we can go through this and calculate delta H, reaction. This is going to be negative 635.1 plus negative 393.5 minus, all the coefficients are 1 here, negative 1206.9. Okay, so delta H, I'm going to put that over there. This is equal to 178.3 kilojoules per mole. All right, then delta S for the reaction equals, let's see, you got 213.7 plus 38.2 minus 92.9. So that is 159.0 joules per Kelvin per mole. And convert that to kilojoules. So this is 0.1590 kilojoules per mole. And then you got to divide by Kelvin too, per Kelvin. So now they're both in kilojoules. You got to do that. All right, then the next step would be to calculate delta G for the reaction. And of course, this is the case of positive, positive, positive enthalpy and positive entropy. So the delta G for the reaction, you can calculate it either way. You can say 178.3 minus temperature standard, because of the little zeros there. The numbers in the table are associated with 298 Kelvin. So times 298.15 times 0.159. And I didn't put the units in, but all the kilojoules kelvins cancel, and this is going to be kilojoules per mole, so this will be plus 130.9 0.9 kilojoules per mole. So you got positive, positive. It is non-spontaneous because it's delta G is positive. So it's non-spontaneous at 298 Kelvin. If you heat it up, it's going to become negative. Now, if you go back to the criteria, this 130 right here is greater than 10 kilojoules, so greater than 17 kilojoules as well. Greater than 10 kilojoules, therefore it's non-spontaneous. Positive, it's non-spontaneous. All right, non-spontaneous at that temperature. All right, now if we, let's see if this is gonna work. Okay, there we go. Continue along. The problem was to do it at 1,273 Kelvin, which is 1,000 degrees C. And if we did that, we'd have 178.3, and this is the first time, no, I'm sorry, the last problem we did this too. Yeah, it's not normal to put in temperatures other than 298, but for purposes of general chemistry, and also these temperature changes are not that dramatic, it's not completely wrong to put in a temperature other than 298. So we're just going to do it and ignore the consequences. The differences are not that big. So you're going to get negative 24.1 kilojoules for delta G at 1,000 degrees C. So now at 24, this is less than 10 kilojoules, right? Less than negative 10 kilojoules. My notes are wrong there. And so it's going to be spontaneous. Right? Because delta G is negative means spontaneous. It means the reaction will. All right, and then what else? So we can calculate Kp at 1,000 degrees C or 1273 Kelvin. So again, it's not technically 100% correct, but we're going to do it anyway. ln K, Kp there, is equal to, hold on, delta G is equal to negative RT ln K, and then K, ln K, will be equal to delta G divided by RT, and so this is negative 24.1 kilojoules. We're going to go to joules here, 10 to the 3rd joules per kilojoule. And that's because we're using R 8.314 joules per mole per Kelvin and multiplying it times 1273 Kelvin. So natural log of K here equals 2.277, and remember, you got to practice these problems yourself. It's easy to make mistakes, especially if you're putting negatives or positives into the equation. And you have two negatives here, actually. So you get the negative from here, and also delta G is negative, so it's actually times negative again. So this is going to be, that's positive right there. We can check that. I think that's right. Okay, so then that's going to be positive 2.77. Take e to both sides, you're going to get 9.75. And then that's pretty much the answer here. This is Kp. And you could write down the expression for, well, you could just K in general. Let's just have a look at that. So this is calcium oxide. And remember, when you have a mix, calcium oxide was solid, CO2 is a gas, so you put pressure and atmospheres in there. And then calcium carbonate is a solid as well. So you remember the convention that pure solids are going to be equal to 1, their concentrations are equal to 1. So then K is equal to the pressure of CO2. And that will be equal to 9.75 atmospheres. So K is 9.75, and then, didn't ask for it, but the pressure is 9.75. You could write that down twice. Okay, so let's see, last page of notes here. And let us look at, we want to find the conditions where the reaction changes from non-spontaneous to spontaneous. And so you have delta G is equal to 0, which is equal to delta H minus T delta S. So solve for T. Just memorize this equation here, delta H divided by delta S. Kind of an important one. And that's your transition temperature. So here we're going to have positive 178.3 kilojoules and divide by 0.1590 for the entropy kilojoules per Kelvin. And this is going to be 1121 Kelvin, and that corresponds to 848 degrees C. Big mess there. Going too fast. All right, so 1121 Kelvin is the transition temperature. So for this one, we can summarize and say that when the temperature is 1,000 degrees C, which is 1273 Kelvin, delta G is negative 24.1 kilojoules per mole. And this is going to be spontaneous. That's actually less than negative 17, right? So that would make it spontaneous. And then at 848 degrees C, which is 1121 Kelvin, delta G is 0. That's the transition temperature. And then at 25 degrees C, which is 298 Kelvin, we have positive 130.9 kilojoules per mole. And it's greater than positive 17, so that's going to make it non-spontaneous. Non-spontaneous at the low temperature. All right, so then you heat it up. It goes from non-spontaneous to spontaneous. All right, I think it was worth it to go through these two examples. It kind of ties together a lot of different topics that we looked at individually. Maybe you get the big picture from these. So, all right, that's the end of the Thermo chapter. And next is electrochem.